In this screencast, we will discuss solutions to test 1. So in order to understand this discussion clearly, you may need to have your exam, so a copy of your exam. So we start with question number 1. So question number 1 asks like 3 of the questions that are listed there requires to find or to evaluate limits algebraically. So the first question is to compute the limit of the square root of x minus 1 over x minus 1 as x approaches 1 algebraically. So when you plug in x is equal to 1 in the denominator, you will get 0. Therefore, so in order to evaluate this, we should be able to eliminate x minus 1. So one way to do this is to multiply top and bottom by using the conjugate of the numerator. So so the conjugate of the numerator is the square root of x plus 1. So we multiply top and bottom by this expression. So therefore, as a result, we'll get x minus 1 over x minus 1 times the square root of x plus 1. So the x minus 1 will cancel each other. So therefore, as a result, we get this expression. So therefore, at this point, we can plug in place of x is equal to 1. So we get this result. So so the answer will be 1 over 2. So the important thing in this limit computation is you should also pay attention how to write your solution in more logical, sequential order, clearly and completely, and especially note the style about the use of appropriate notations in the solutions, like the use of equal sign and the use of limit appropriately using this. So the common mistake that I see is that sometimes students write limit here after even they plug in. So writing this is wrong there, basically, because you already evaluated the limit by plugging in x is equal to 1. So therefore, you should practice how to write your solution in more clearly using appropriate mathematical symbols in a complete, clear way. So, and that is one of the objective of or the goal of this course, to be able to communicate your solutions in more clearly, so that anyone who is reading your solution can understand more clearly without any doubt or confusion. So that is the goal of the course: writing skill, mathematical solutions in more understandable way. So this is one way to do this problem. And alternatively, instead of like using conjugation, one can also use the following, like instead of conjugation, we can rewrite this as an expression which involves the square root of x, so that it look like the top. So one way to do is that x is the same as the square root of x squared minus 1. So therefore, this is the difference of two squares. So we can now factor. So as a result, we get the numerator. On the numerator, the square root of x minus 1. In the denominator, the square root of x minus 1. So the two will cancel. So as a result, we get this expression. So like as the first solution, so we can plug in x is equal to 1 in this expression to get the answer 1/2. So therefore, this is a complete, logically written in more sequential manner using appropriate mathematical notation. So my expectation will be similar on your second test. So even, in fact, I am writing this solution to help you to show my expectation, especially in writing skill. Okay. Now 1b. So it is the same as almost problem number 1 in a sense that in the denominator, when you plug in x is equal to 3, it will make the expression undefined. So because of this, in order to evaluate this limit as much as possible, we should be able to get rid of this. So one way to do this is to simplify more the numerator. So one way to simplify is to combine these two expressions using common divisor. So therefore the least common divisor will be 3x. So you multiply the top and the bottom of 1 over x by 3 and 1 over 3 by x, top and bottom. So you will get 3 minus x over 3x. So this can be rewritten as, to make it look like this, you can rewrite 3 minus x as negative x, negative times x minus 3. So negative 1 times x minus 3. So as a result, we get this expression. So the x minus 3's will cancel each other. So therefore, you get negative 1 over 3x at this point. So we can plug in. So as a result, we get negative 1 over 9. So this is one way to do this problem. And the other alternative way to do this problem will be, instead of combining 1 over x minus 1 over third, you can multiply the top and the bottom by 3x. Then eventually it will reduce to negative 1 over 3x using cancellation. So this is the way to do 1b. 1c, similar to the other two problems. So when you plug in x is equal to 3 in place of x, again we'll have division by 0. So the goal is to eliminate this expression x minus 3 using appropriate algebra. So one way to do is, so to get the expression x minus 3, one can see that if you factor the thing in the absolute value, you get 2 times x minus 3. But we cannot cancel x minus 3 here because the expression in the numerator is with an absolute value. So because of this, we have to simplify more. So the product of the absolute value of the product is the product of the absolute values. So which gives us 2x times the absolute value of x minus 3. So at this point again, we cannot cancel x minus 3 because 1 is within the absolute value. So to eliminate this absolute value, we have to be able to distinguish what is the sign of x minus 3 when the values of x are in the neighborhood of 3, meaning when x is less than 3. In that case, we need to find what is this, the absolute value of x minus 3. It will be itself whenever x minus 3 is non-negative, which means when x is greater or equal to 3, and it will be the negative of x minus 3 whenever x minus 3 is negative, which means when x is less than 3. So, but since we are interested for the values of x when x approaches 3 from the left, in that case the value of x is less than 3, so we take this branch. So therefore the absolute value of x minus 3 is this object, the negative of x minus 3. So we replace the absolute value by that. So as a result, now at this point we can cancel x minus 3. Then we take the limit. So as a result we get negative 6. So this is just this problem in the to see in big picture of this. It requires the ability to manipulate absolute values. That is all in this problem basically. Other than that, the technique is similar to A and B. Okay, so this is problem number 1. Now when you problem number 2 asks about your understanding of the concept of continuity, especially the definition of continuous function. How can you use it to solve problems related to this? For example, in problem part A. So we are given a function as a branching function. So for x different from 2, f of x is this, and for x is equal to 2, f of x is equal to k. So the question is, what should be k so that f of x is continuous everywhere? So clearly, for x different from 2, the function is clearly continuous because it's a rational function where the denominator cannot be 0. So therefore, f of x to be continuous everywhere, it should be continuous at this point, at the branching point, x is equal to 2. So what does it mean the function is continuous at x is equal to 2? That means we require that the function to be continuous at 2, this condition should be satisfied. So therefore, the problems boils down manipulating what I wrote in this yellow box. So f of 2 is k, it is already given, f of 2 is k. So therefore, k must be the limit of f of x, the limit of this function. But what is this function when x approaches 2? X approaches 2 means x is different from 2. X is different from 2, the value of the function f of x is this one. So therefore, we replace f of x by this expression. So then we factor negative 3x squared from the top with the goal to eliminate x minus 2 because we cannot plug in x is equal to 2 at this point. It causes division by 0. So therefore, as a limit as x approaches 2 of negative 3x squared will be negative 12. Therefore, k should be negative 12. So the value of the value of k that makes the function continuous everywhere will be negative 12. So therefore, so this is the idea. So the important thing here is like how you should write your solution in more sequential, logical order in a complete mathematical sentence. So this is the requirement of this problem, basically. You should be able to communicate your solution in more detailed and more rigorous way so that anyone can understand it more clearly and in more detailed way. Okay, so part 2, a similar problem, but in this case, now we have a branching function where we have top and bottom one. The top one is polynomial, the bottom one is, meaning the top one is quadratic polynomial, and the bottom one is linear polynomial. Clearly, both of them are continuous functions, but f of x to be continuous everywhere, it should be continuous at exactly at 2 also. Clearly, it is continuous for x less than 2, for x greater than 2. So the problem is, how about when x is equal to 2? In that case, we require this condition to be fulfilled. This is the condition for the function to be continuous at 2. So the problem boils down to manipulating this yellow box. So we compute each case. So the limit of f of x as x approaches 2 from the left. This is clearly this from the left because x is less than 2. So then to compute this limit, we plug in place of x2, so we get that. And similarly from the right, and f of 2 is we take this branch because x is equal to 2 means 2 times c minus x, so we plug in place of x2. So therefore, in order to f to be continuous everywhere, these 3 objectives should be equal. So therefore, we equate these 3 objectives in principle, like this is the same as that. So basically, we equate these 2 and we solve the resulting equation. So therefore, we have to set this to equal, so the function to be continuous. So then the problems boil down to solving a quadratic equation. So this will cancel. So therefore, c squared is equal to 2c. So some students have struggled to solve this. And some of the students used this kind of algebra, dividing both sides by c. But the problem, we cannot divide both sides by c because c is not known. We cannot divide by something that we don't know. So because of this, this approach is wrong, because c is not known. It can be 0. Division by 0 is not allowed. So therefore, the appropriate algebra will be bringing 2c to the same side as c squared, then factor, then the product of these two objects is 0, means either one of them is 0 or both of them are 0. So therefore, c is equal to 0 or c minus 2 is equal to 0. So when you solve each one, we get c is equal to 0 or c is equal to 2. So therefore, these two values of c will make the function continuous everywhere, which can be verified by plugging in place of c the numbers we got and plotting the curve. Then one can see clearly the graph has no hole, everything, and it is clearly continuous function. Okay, so that is all about number 2. And number 3, we are given one function g of x as a graph, the other one as an algebraic expression. So the problem is finding the limit of the product. So to find the limit of the product, we cannot plug in place of x1 because division by 0. And also, since g at 1 is 4, we cannot plug in place of x at this product. So therefore, the idea is to be able to split the limit using property of limit. The limit of the product is the product of the limit. But in order to split, we have to first make sure each limit exists. That is why first we have to do the limit of this, the limit of that. Then once both limits exist, then we can split and substitute in place of each limit the value we got. So this is obtained from the graph, and the other limit is obtained by factoring. And one of the challenges that I saw some of the students have hard time factoring this, which requires like a difference of 2 cubes. So x cubed minus 1 means it is the same as x cubed minus 1 cube. So you use the difference of 2 cubes formula to split or to factor x minus 1 like this way. Then x minus 1 will cancel. As a result, we get this quadratic expression. At this point, we can plug in place of x1, so we get the result. So therefore, we have to note at this point, like the expectation, my expectation from you, how you present your solution in more detailed and in more mathematical sentence, and the style of writing, use of appropriate symbols, and how each line follows from the previous one. So this is the expectation from you from this course. Especially writing skill should be emphasized, especially when you do solution. It is not only getting this answer, the important thing is the intermediate steps are very important. Okay, so 3b, in this case, it asks at what point that the function is not continuous. So the only point that the function is not continuous is at 1. So most of you got the answer this, the function is not continuous at this point, but the problem is how you justify g is not continuous. In this case, the problem asks you to use the definition. Like intuitively, the function has a hole or a jump is not appropriate in this case. Use the definition means limit definition. In this case, we have to verify whether these two objects are equal or not. So in this case, we compute the limit of this from the graph. Again, from the graph, as you can see, 3 is different from 4. Therefore, g is not continuous at x is equal to 1. And this completes number 3. And number 4, in this case, the limit as x approaches infinity of this object. So in this, so when you evaluate the limit which involves infinity or minus infinity algebraically, in this case we have to pull out x cubed to get expression of this form, because in order to evaluate the limit, so when x get larger, a number over large number, so 8 over large number get closer to 0, the same thing 2 over large number get closer to 0. So this will be the answer, -1 from here. So that is one way. So I think almost all of you got this answer. And part B, also similar question, but we have here radicals. So the idea is again like problem number 1. In this case, one way to do this problem, as I said, you divide the top and the bottom in principle by the highest exponent of the expression. So, but for the second part, in order to do this problem, again we pull out x squared, like the way I identified. So therefore we get the square root of x squared times 3 over x squared plus 8. So this is multiplication. So when the square root of x squared is the absolute value of x, so again we pull out x from the bottom also. But at this point, unfortunately, we cannot cancel the square root of x by x. We should be able to remove the absolute value. So therefore, in this case, paying attention here is very important. So as x gets closer to negative infinity, the values of x are negatives. So when x is negative, the absolute value of x by definition is negative x. So we replace the absolute value of x by negative x. Then we proceed to the simplification of the algebra. Then as x gets to minus infinity, 3 over large number goes to 0 again, and 2 over large number goes to 0 in negative sign. So therefore, as a result, we get 2 times the square root of 2. So therefore, this completes number 4. Number 5, question number 5, we are given the graphs of f and g. The graphs of f and g. So now problem number 1 asks you to find this limit. So one way to do is, since f of x is not known, it is just its graph. So therefore, we should be able to split this limit into 2. So like this. So in order to split this, before we split, we have to make sure each limit exists. So that's why I have done first, before I come to this step, compute the limit of this, which is obtained from the graph, and compute this limit using algebraic technique. So the limits both exist. So we replace each one by its value. So as a result, we get 4 normal. So this is 5a, and 5b asks how to compute the limit of this. This was the question. So to compute this, again, g of x is not given, it's given explicitly, but it is given in terms of graph. So from the graph, we compute the limit from the left, the limit from the right. So in this case, the left and right limits are not equal, so therefore the limit does not exist. And pay attention how I wrote the solution. It should be more complete. For example, where do these two values come from? I just said from the graph. So we get this. So this is a complete mathematical sentence that the reader have no doubt or confusion in order to understand the solution. Okay, so this is my expectation in terms of writing. So the same holds for 5c. So the question is, compute the limit of the ratio of f over g. Since f over g is not given, f and g are given in terms of graph. So the idea is to split this limit into using quotient rule, the limit of the numerator over the limit of the denominator. In order to do this, to apply quotient rule, the limit of the top and the bottom should exist, and the bottom should be different from 0. So that is what I did first before we split. So basically, so once we do that, we then apply the quotient rule to get the answer. And similarly, 5D, the question is to compute this limit. So in order to compute this, we cannot just simply plug in 3 here, because the graph of 3 times f of x is not given, the graph of 2 times g of x is not given, the graph of the sum is not given. So because of this, first we split appropriate using addition rule, then using constant multiplication we pull out 3, then at this point we compute these 2 from the graph, which I have done it first. So once you make sure that the limit exists, then we plug in the result that we got to get 18. So this is number 5. Now let us go to number 6. It is a true-false question. So the first true-false questions ask basically, if you know the limit of f of x, and if you know the value of g at 2, can you conclude the limit of the product as x approaches 2 is 12? This may not be true necessarily, because even we don't know how 12 comes. It seems like it is multiplication by 3 by 4, but in that case we cannot plug in place of x2 in this case, because we don't know whether the limit of each exists. So therefore this may happen that the limit of g of x as x approaches 2 may not be equal to 4. So because of this, one counter example will be to construct g of x so that the limit is not equal to 4. So, but g at 2 is equal to 4. So in this, this is one typical example, for example, counter example. So as much as possible, you should make your counter example as easy as to understand in more clear way. So you can give graphically, or you can give like explicitly like this. So I took just a simple function. You see, like at 2, it is 4. Otherwise, it is 2 everywhere. Everywhere it is 2. So this function, you see, if has a limit at 2, but the limit is different from 4. So when you split the limit, we don't get 12. So we get different answer. So because of this, this is a counter example. Again, counter example means an example which satisfies the if condition, but it does not satisfy the then part of the statement, basically. Okay, so this is one counter example. And 6b, it asks us, if you know the limit of f of x as x approaches 2 is equal to 3, can you conclude the value of the function at 1.99 is closer to 3 than f of 1.9? So the existence of the limit at 2 it is 3. But from this limiting value, we may not conclude anything about the closeness of the value of the function at 1.99. So f of 1.99 may not be closer to 3. May not be closer to 3 than f of 1.9. For example, this, this is one counter example. So f of 1.9 is exactly 3. F of 1.99 is almost equal to 4, exactly 4. So clearly 4 is not closer to 3, so clearly. So this is one condition. It satisfies the hypothesis, but the conclusion is false, meaning f of 1.99 is not closer to 3. So the idea of this question is that in order to help you understand what does it mean, the limit as x approaches to f of x is equal to 3. This means from this from this, one cannot conclude what is the value of f of the relationship between f of 1.9 and f of 1.99. So therefore the statement is false, and this is a counterexample, one counterexample. And 6C asks us whether we can split the limit of the product of two functions as we wish. No, we cannot split the limit of a product, meaning the limit of the product of function is not the product of the limit, as I said before. In order to split, the limit of each component should exist. So if the limit of either of the components, if it does not exist, this sentence may not be true. So this is what I gave. So clearly construct a function where the limit at 1 clearly at g of x and f of x does not exist. But when you multiply f and g, the graph look like, the graph of the product look like this. So for x greater than 1, f of x is 1, g of x is 0, therefore it will be 0 for x less than 0, and it will be 0 for x greater than 1. So therefore this is g of x, f times g. This is the graph of f times g. So the graph of f times g is everywhere 0. So the limit of the product is 0, but the limit of f of x as x approaches 1 does not exist. The limit as x approaches 1 of g of x does not exist. So clearly the limit of f of x as x approaches 1 times the limit of g of x as x does not make sense. So because of this, this is a counterexample where we cannot split the limit. The two sides are not equal. Okay. But as a remark, when will be the two sides equal? The two sides will be equal, meaning we can split limits provided each limit exists. Provided each limit exists. Okay, number 6. Number 6 says, if the limit of this is 3, can you conclude f of 2 is 3? Not necessarily. So f of 2 can be anything, or even if it may not be even defined. So a good counterexample may be like this. This is one. Of course, there are several counterexamples we can give. F of x is 3 everywhere except 2, and at 2, f of x is 4. So the limit of f of x as x approaches 2 is 3, but the value of the function at 2 is 4, different from 3. So therefore the statement is false, and this is a counterexample. And number 6, also, if you know the limit of f of x as x approaches 2 and the limit of g of x as x approaches 2, if both of them goes to 0, can you conclude that the limit of f over g as x approaches 2 does not exist? Not necessarily. It may exist. For example, take f of x is equal to x minus 2 square and g of x is equal to x minus 2. So the limit of each of the given function, it is 0, 0. So it satisfies the hypothesis, but the limit of the ratio, it becomes x minus 2. As a limit, it is equal to 0. So the limit, in this case, it exists. So therefore the given statement is false. So this is a counterexample. So from here, you should learn how you can give a counterexample and how you can argue your reasoning. So this is just how do you give your reasoning in more complete logical sentence, which is very clear for the reader. So that is all about the solution for test 1. So hopefully, I hope from this you learned a lot, and for test 2, based on this experience, I expect that you will perform well on test 2. Okay, so thank you for listening.